a very long time. Thank you, Lorenzo, and thanks first of all to all the organizers for organizing this fantastic event in this great location, and for giving me the opportunity to talk here. So today I'll be telling you about some work that I'm doing in collaboration with Melissa, Mrinal, Balsam, Jack, and Gavin on extending the methods of Jack calculus to next linear log, and I'll tell you why we want to understand this type of problems. This is mainly based on a recent paper and ongoing work that we're still working on. So, what is the motivation? It's sort of twofold. On the one hand, there are classes of resummations that don't admit an analytic closed form. There are many problems of this type. This is either due to the nonlinear nature of evolution equations. Examples are microjet fragmentation, fragmentation of small r jets, or non-global logarithms, or to the fact that the measurement function doesn't have an analytic form, for instance, some event shapes or jet rates. In that case, we cannot tackle this problem with standard analytic techniques, and numerical methods are an effective way to understand how to resum some of these observables. The second reason why we're interested in this, and arguably the more important one, is that there is an ongoing effort towards understanding how to improve the accuracy, the logarithmic accuracy of Barton showers. Now, in the last 5 years or so, people have understood how to build next-to-linear logarithmic algorithms. By that, I mean that they resum across the board observables belonging to certain classes, what we normally call recursively infrared and collinear safe, and some classes of non-global observables. Building these algorithms is done based on constraints coming from QCD, so requiring that the multi-parton amplitude squared are reproduced in those problems as they should, as well as consistency with QCD resummations. Now, going beyond next-to-linear log, of course, brings in, as many of you know, a number of additional subtleties, like the treatment of virtual corrections that normally come in dimensional regularization, as well as the cancellation of IR singularities between reals and virtuals becomes more subtle. So having a framework that sort of solidly bridges between resummations and Barton showers is quite instrumental for us to study features of the shower evolution, like the presence, for instance, of infrared cutoffs, and gain some deep insight on how to construct, at some point, algorithmic solutions beyond the next-linear logarithmic order. So the outline of the talk is the following. I will take a little step in that direction and focus on collinear fragmentation. By that means that I'll be considering problems that in some proper organization of perturbative expansion admit a single logarithmic series of terms. So the single logs that are the linear logs in my problem, they are normally next to linear logarithmic in double logarithmic observables, and the next to single logs that what I'll be focusing on are next to linear logarithmic terms in double log observables. And I'll be tackling the resummation of these terms for this class of problems. So these are observables that are exclusively sensitive on collinear divergences, collinear logarithms, using an old method that is called the generating functional method. I will briefly summarize. And I will explain it in the context of an explicit example looking at some observables, so-called fractional moments of energy correlators and angularities measured on groomed jets. I'll discuss how, in this example, how to connect an analytic solution to a more standard Markov chain, Monte Carlo, that is what one uses in a Barton shower context. And then finally, say a few words about the extension of these formulas to next to single log. And again, if I have time, discuss the application to the same class of observables. So let's start with the simple case of single logarithmic fragmentation, and then we will discuss later how to move to next single log. So some definitions. Now, generating functionals method, this is something that was first proposed in a series of papers by Konishi, Ukawa, and Veneziano back in the late 70s, and then it was used after that in many contexts by many people. For instance, a nice review can be found in this book. So it postulates that there exist 2NF plus 1 generating functionals in a theory with NF fermions, GFs. These are abstract objects that describe the fragmentation. In this specific case, I'll be considering time-like fragmentation of a parton of flavor F that carries a fraction x of the initial energy E of the jet, starting at initial evolution time that I'll define shortly, and all the way down towards lower values of the resolution scale, up until non-perturbative scales. Now, how do we choose the evolution time? So to understand this, we are trying to organize the resummation of the perturbative series in ways that are very different from what is done in other approaches to resummation. And specifically, what we want to do is we want to reconstruct the squared amplitude in the collinear limit, in the limit where, in a case where we have n particles in the final state. And in the specific process at hand, for instance, we know that the squared amplitude in the limit where we have n strongly ordered emissions strongly ordered in angle is just a collection of leading order splitting functions. So that can be reconstructed, for instance, by ordering these emissions either in angle or in the kT, whereas between the emission and the emitter. And so either of these two is a legitimate choice for the evolution variable. Once I know the evolution variable, in this case angle, for instance, that's what I'll be using here. I calculate the evolution time that is just adding information about the running of the coupling. Now, once we have that, this calculus calculates the probability of observing a state with exactly m partons by taking m functional derivatives of these generating functional objects with respect to a quantity u that is called a probing function, or the source in the standard functional integral formalism. And this is a function of the kinematics of the emission that we are tagging, as well as its quantum numbers, for instance, flavor in this case. Once you've done that, you have a collection of these exclusive emission probabilities. You calculate an observable due to the fragmentation of a parton of flavor F as some perturbative matching coefficient function that matches the collinear description of the generating functionals to full QCD, and this function J that is just an infinite sum over all of these exclusive emission probabilities. Okay, each term is then weighted with the observable's measurement function. Now, a second piece of information that we need is to define these G objects is how do they behave, how do they change when we change the value of the evolution time. And it turns out that they satisfy a set of evolution equations that in the single log case has been derived long ago, for instance, in this paper. So let's go through it in graphic form. They are a little bit nicer to understand. So they say that the generating functional for the fragmentation of a quark starting at a resolution scale t is equal to the probability for that quark not radiating anything between the scale t and some non-perturbative scale t naught that acts as a collinear cutoff, plus the probability of not radiating up until a scale t prime, at which point the quark splits into a quark and a gluon, and then the quark and the gluon further evolve with their own generating functionals, okay? The gluon now has a similar evolution equation, of course a little bit more complicated due to the fact that you have two splitting channels, but is very much the same physics. Now you see from this evolution equation that the two, the quark and the gluon, and similarly for the antiquark that is obtained by charge conjugation, these are very nonlinearly coupled equations, and therefore it's very hard to solve them in closed form in the general case, of course. So one can, however, show that under certain conditions on the kernel, these equations admit a solution that can be obtained by acting an infinite number of times recursively with this integral operator on the right-hand side on some initial condition, okay? And equivalently, you can also bring them into a boundary value problem and try to solve the differential equations in that case. Now, let me make a few remarks on this result. So the first one is this object, the Sudakov form factor delta that, as I said before, describes the no emission probability. This is a very crucial concept in the field of Barton showers, in that it tells you essentially how to generate emissions in a Markov chain algorithm. So the definition of the Sudakov delta is encoded in these equations, and it can be read out by essentially just imposing the constraint of unitarity. That means that if I have an infinite number of collinear radiation and I integrate inclusively over the phase space, I want the cross-section not to be affected at all by this ensemble. It's just a way to state the K-length theorem. So when I set the source U to 1, so I'm fully inclusive, the generating function has to be normalized to 1. So if I put 1 in this equation, solve for the Sudakov, I get out the expression for the Sudakov factors of a quark and the gluon, and they take this simple form at the single logarithmic level. And this is a trick that can be repeated at all perturbative orders, also when I extend this to next single log. A second comment concerns the regularization scheme. As you can see here, I'm using some cutoffs. I'm regulating collinear singularities with an angular cutoff corresponding to time t0, and the soft singularities with an infrared cutoff z0. I could well proceed directly with dimensional regularization and go through the calculation in DIMREG and only take epsilon to 0 at the level of physical observables. That would work, although it's very complicated to do. But the reason why I'm using cutoffs is that first of all, I'm interested in solving these equations numerically in a computer, so I want them to be finite in, well, finite for dimensions. But also that's what a Barton shower would be doing. So by formulating things in this way allows us to study sort of interesting effects due to the fact that we're working with a cutoff in the context of a shower evolution, for instance, where we calculate a fragmentation function or observables of this type. The third comment I want to make, so I'll be always working with this cutoff regularization, but physical observables are strictly obtained in the limit where I relax these cutoffs. So I send the collinear cutoff to infinity, or the angular cutoff to 0, and same for the soft cutoff. And modulo regularization of the Landau pole, that's I will understand that, so my results will be understood in this limit. And I will consider, of course, the Landau pole to be a much smaller scales than where the observable lives. So non-perturbative effects are irrelevant in this respect. Third comment concerns the ordering. As I said, the choice of ordering is related to the fact that I'm just constructing a multi-parton squared amplitude recursively. So any ordering that allows you to do that is in principle viable. In this case, I'm working with time. Transmomentum is also a legitimate choice for collinear fragmentation. For instance, in other cases like soft evolution, soft wide angle, this is governed by similar equations, but that actually involve color dipoles in the planar limit instead of individual partonic propagators. And in that case, for instance, you can show that a choice like angle wouldn't reproduce the correct square amplitude, and therefore would lead you to the wrong result. But as long as you are careful with that, the physical result should not depend on the choice of ordering. If it does, there is something wrong in what we're doing. So let me explain this a little more concretely in an example. I'll be considering some class of observables that is fractional moments of EC and angularities. These are observables that are defined in this way. These are common event shapes. So they admit a double logarithmic perturbative series. But I consider a special case where I measure them on groomed jets. So I take a jet and I apply modified mass drop or soft drop with beta equal to 0 grooming. That is, I organize the jet as a sequence, a list of the clusterings ordered in angle according to the Cambridge algorithm. And then I go through the declustering starting from the guy at bigger angles. And when I meet at the clustering, I ask whether the branching satisfies some grooming condition, that is, the energy fraction carried by the branching is larger than a certain threshold Z cut. If it is so, I stop the grooming, that's my groomed jet, and I calculate the observable on whatever is left. If it's not the case, I get rid of the softer of the two objects in the branching, and I move on to the next branching in the angular order history. Now, this kind of thing leads to two important simplifications. The first one is that it makes my observable single logarithmic, so they kill soft logarithms completely. So I only have collinear logs left, and therefore they now belong to this class of collinear observables that I'm studying here. The second simplification is that these observables are recursively infrared and collinear safe, so one can show that if you have a jet, if you take a number of primary declusterings of a jet that are declusterings emitted off the harder subjet, secondary branchings of those declusterings, for instance, further splittings, are suppressed one logarithmic order down with respect to the primaries. So what that means is that at the single log level, I can approximate the problem in such a way that the secondary declusterings never, the secondary splittings never happen. So for instance, if I'm considering a quark jet, the quark radiates gluons and assume that those gluons never split. That means that I can approximate the gluonic generating functional with just this first order expansion in alpha SU and neglect all relative corrections. So now this equation for the quark is much simpler and actually can be solved analytically. So what you can do is, for instance, you can take the definition of a physical observable. Yes?
Did you say how suppressed the triple collinear splittings are?
Yes.
That are not iterations of double collinear?
Very good, yes. So in this case, the single logarithmic order is due to the emissions strongly ordered in angle. So in that approximation, you only have single splitting functions iterated. Then at the next single logarithmic order level, you will have two emissions that are close in angle, and at that point, the 1 to 3 splitting function will come in. And I'll show that in a second. So to calculate these observables, for instance, I'm interested in the cumulative cross-section. I calculate the cross-section by summing over these exclusive emission probabilities, and you can obtain these PMs by acting with the functional derivative. You obtain, for instance, this kind of expressions for the first 3 terms in the series. Each of these is now weighted with the value of the measurement function. For instance, if I have only the quark in the final state, no additional emissions, the observable is trivial. If I have a quark and a gluon, the gluon contributes to the observable in the collinear limit, so I'm expanding the observable in the collinear limit. If the branching is resolved, so is above Z cut, so it satisfies the grooming condition. If it doesn't satisfy the grooming condition, that the gluon or the software between the quark and the gluon is discarded, and then what I'm left is a single part, and that again is a trivial contribution to the observable, and you can iterate this with additional emissions. So you end up with a picture where you have one emission that fixes the value of the observable, so it goes into the delta function, and everybody else in the event is either happening at smaller angles, so it's not captured by the grooming, or it happens at larger angles, but it has a Z below Z cut. So it's something that doesn't satisfy the grooming condition, and therefore it gets discarded by the soft drop algorithm. So you can now factor out the observable, the emission that sets the value of the observable, and sum up the rest, and you obtain a nice exponential function. Then finally, if you want the cumulant, you integrate over Fc sub x, and you obtain this kind of very simple expression. So you can now relax the cutoffs, and you end up with a standard resummation, a single log for this type of groomed event shapes. So of course there are other ways, perhaps better ways of doing this type of calculations with other techniques, but you can get there from this type of approach. Now what is interesting is that I can also get to this result in a very different way using the same equations, and that is by massaging a little bit the equations. For instance, I look at the probability of observing a quark as the probability of an initial quark not emitting between a scale t and a scale t naught. The probability of seeing a quark and a gluon is the probability of a quark not radiating between t and a scale t1, at which point it radiates a gluon. and then the resulting quark doesn't emit anymore between T1 and T0, and so on. So this is a simple Markov chain problem, and by noticing that the emission probability is just organized in terms of total derivatives, you can map this problem, the resummation of this series, into this very simple Sudakov problem where you solve the ratio of Sudakovs evaluated at scale Ti and Ti plus 1 equal to a random number between 0 and 1 for the next evolution time in Ti plus 1 that tells you where the next emission is going to happen. You just solve recursively until the scale of the new emission goes above the collinear cutoff, okay? So this whole complicated problem boils down to this super simple equation that is trivial to solve in 10 lines of code, and most importantly, this is exactly what will be going on in a shower. So the beauty of writing things in this way is that from the same equation or set of equations, you can start from there and make your way through towards a resummation, or write down a shower algorithm that solves the equations, and so it bridges essentially the two areas of these two areas of QCD. And what that means is that we can gain very deep insight on how to formulate a shower by playing around with this type of formulas. That also means that if we want to develop next to lean log showers, we can at least try to gain some mileage by extending this whole business to next to single log, and then apply this to see what kind of information we can get out of it. So to go to next to single log, that's what I'll discuss in the next 10 minutes. I'll go a little bit over time. So let's see how to do that. We'll look at the master formula that I wrote before. There is an easy piece and a less easy piece. The easy piece is this matching coefficient, say, that I consider at 3 levels, so in the trivial order at single log. Now it needs to be calculated at the 1 loop level. So this is something that is obtained by matching whatever the generating functional gives you to full QCD. That matching is fully perturbative, so it's just a series in alpha S evaluated at the hard scale of a process if we consider an infrared stable observable. So this is an observable dependent thing that can be calculated. Normally it's an easy calculation. In the context of shower Monte Carlos, this should be captured by NLO matching. So there are different consistent ways of deriving this type of contribution. Now the less easy piece is that the J, that is just an infinite sum over exclusive emission probabilities that in turn are obtained as functional derivatives of the generating functionals. Now the generating functional evolves according to a 2-loop integral evolution operator that is just different from this logarithmic one that was just at 1 loop. So to see what that entails, let's look at the form of the quark evolution equation, for instance. And I'll just consider the non-singlet channel of a quark fragmentation in a very simple color configuration that is CF squared, so only a billion emissions of a quark line. So the first term is the Sudakov. This encodes the virtual corrections. So we're obtained for free at single log by imposing unitarity, and as we will see in a moment, that is also the case at higher logarithmic orders, like next single log. The second term here, this at single log included the single splitting function. And notice that the structure of generating functional is that it says 2 generating functionals corresponding to the fact that I have both a quark and a gluon in the final state. Now, if you aim at computing NLO corrections to this kernel, you need to add 1 loop corrections to the single emission splitting function. And this term will also be proportional to the 2 G's, the G of the quark and the G of the gluon, okay? For the moment, let me consider this to be dimensionally regulated. Now, the second piece is, this is where it gets complicated, is the double real correction. That's where the 1 to 3 splitting function comes into play. So the double real correction will have a term that is precisely proportional to the full matrix element that now describes a configuration of 1 to 3 splitting with all angles being commensurate. And this differs from the previous term in that it brings a new structure that was absent at single log level that is proportional to 3 generating functions, that of the quark and the 2 gluons. Okay? Now from this, noticing that this is a recursive equation, so it iterates, I need to subtract also the iteration of the one loop kernel so that I eliminate double count. And this is a simple thing to do. It just requires the first iteration of the single logarithmic evolution equation. Now, and again, if you use DIMREG, this is a very complicated way of stating an evolution equation, but you could, in principle, calculate a physical observable with it. But what I would like to do is to bring this one into a form where it's manifestly finite in 4 dimensions so that we can solve this numerically and eventually solve it using numerical methods like Monte Carlo techniques that are what a Parton-Schauer algorithm would be using. So to do that, we have, of course, a standard obstacle, that is the fact that there is a constellation between reals and virtuals of infrared singularities. And this is complicated by the fact that the 2 contributions live in different phase spaces, 3-body phase space versus 2-body phase space, and also the structure of generating functionals is different in the double real that has 3 generating functionals and the real virtual that has only 2. So to do that, we can use standard subtraction techniques. This is just a very simple NLO problem. So our reals here in red and our virtuals here in blue. So we can introduce a kinematic mapping that takes the 3-body phase space and maps it onto the 2-body phase space, hence taking this real integral and obtaining an equivalent subtraction term that now is mapped onto the 1 to 2 phase space. So it has the same structure of generating functionals as the real the virtual contribution. So of course we need to add and subtract this term, so we add a 0, and then we can combine the guy with the minus with the reals and the guy with the plus with the virtual. The guy with the minus is organized in a way that cancels the singularities of the real, and therefore this whole contribution is finite in 4 dimensions, and the piece with the virtual can be integrated analytically in d dimensions at fixed 2-body phase space, and you end up with this ingredients that then go into this evolution equation that now is made completely finite in d equals to 4. So we can set 0 at the integrand level and do the calculation in principle on numerically. So this leads already to a number of very interesting observations that are very close in spirit to what a Parton-Schauer would do. And specifically, the fact that the definition of these counter terms that I use here to subtract the divergences depends on this kinematic map M that I use to map the 3-body to 2-body phase spaces. And this is what you would normally do to subtract the divergences also in the context of a shell. So by doing that, you obtain, of course, a different definition of the integrated counter term depending on what mapping one uses. And you end up with different definitions of the building blocks, of course, of this different terms of this evolution equation. An interesting result is that now if we calculate, for instance, the Sudakov form factor, this is a building ingredient of any Parton-Schauer algorithm, we can again impose unitarity, so impose that the inclusive collinear radiation doesn't change the cross-section. This leads to this formula for the Sudakov form factor that contains this, for the lack of a better name, we call inclusive emission probability, that describes the radiation of the splitting of a quark into a gluon and a quark, including its own NLO corrections that now, of course, include all the channels, all flavor channels and color channels. This has a number of familiar features. You have a Casp anomalous dimension that parameterizes the soft singularities, and then this new anomalous dimension B2 that essentially describes the NLO correction to the collinear, hard collinear splitting. And it's a function of Z that is the momentum fraction after the first splitting. So this is a very unusual definition of Z that is not found in any other anomalous dimension in the literature in this type of problems. So it's very peculiar. And of course, it depends exactly on the definition of that mapping that was used to cancel the singularity. So it's the combination of the integrated counter term and the virtual corrections that result in this object here. In our case, we define the mapping by following Cambridge-Aken like the clustering. This is a very convenient way to map out and sectorize the various collinear singularities. So you can organize things in a way that each time you have only a singularity and they cancel between the double real and the counter term. So in terms of subtraction, it's very efficient. The drawback is that phase space integrals for the integrated counter term now will contain a lot of theta functions. So they are ugly to calculate. But in general, a Parton shower will operate with its own mapping. And so this type of anomalous dimension will need to be updated depending on the shower design one works with. So now this type of thing is very nice. Now we have a fully, of course, you need to repeat this for all color structures and all flavor channels, but now we have a fully next to single log extension of the generating functional method. And it's something very useful for two reasons. So we can now try to tackle, of course, classes of resummation of this sort, like fragmentation functions or microjet fragmentation or groomed event shapes like the ones I discussed before. But also we can try to start connecting this type of approach to a shower Monte Carlo, for instance, by devising an algorithm that solves this evolution equation. This is proving to be full of pitfalls, but in principle it's possible, and hopefully we will get there soon. So once we have this, we can now move around. So we can now try to see, okay, here we are describing only collinear evolution, but I want to also include soft modes. So we can try to put together this type of evolution equations with an analogous set of evolution equations that govern the distribution of soft gluons on the celestial sphere, for instance, to solve non-global type of problems. The two are different, and it's an interesting conceptual question of how to put them together. And with this type of technologies, then you can study the aspects of shower evolution, like the presence of cutoff, or how showers cope with different observables, and this type of things that for now at the next to next log level is completely unknown. So we hope that with this, we get very deep insight and eventually then algorithms at that order. And okay, so I'm going to stop here. I wanted to discuss an application, but I'll just stop. So thanks a lot.
Questions or comments from the audience?
Very interesting talk here. I'm wondering if you're supposed to be able to reproduce the next to leading order DGLAP equations by integrating over the right stuff.
Yeah, precisely. That's a good question. That's the first thing that we try to do, and we're working on that right now. And so the hope is that with this type of equation, you get the DGLAP equation, but also at the same time you manage to reproduce, for instance, a slightly different version of it, that is where you describe the fragmentation of small R jets, and it should all come from the same evolution equation that by solving it, you end up with a calculation of the anomalous dimensions for the different problems that, however, have a degree of universality in the fact that they are described by the same collinear dynamics. But that is something that indeed we're looking into.
Simon.
Hi, Pierre. Thanks for the talk. Very fascinating. If you go back, I have a question which is perhaps trivial. Go back to the first slide. It's connected with the treatment of the soft divergence. You have I think at the beginning where you have slide. Yeah, exactly. There is this small g function that somehow I think parameterizes the connection between your time and your soft scale, right? Yeah. And as far as I understand, I mean, you write it here, but then since you are, I mean, this then determines a double logarithmic structure, but since you're using yet you are only interested in collinear logs, and you forget about this from now on. But then I was somehow surprised that I saw this function coming back again at the end.
Yeah. Okay.
So how do you reintroduce the soft, the correct treatment of the soft singularities in order to get a next leading log result?
That's a very good question. Thanks for it. So the reason why this function is inside the coupling is that we know that the right scale in the soft limit is the transverse momentum, and it's something that you can prove on general terms just because of symmetry. Now, since we're working on a collinear problem here, you could in principle ignore that fact and approximate G2 with 1. You just have E theta, which is still a transverse momentum, but it's transverse momentum only in the collinear limit, which will be perfectly fine for the problems at hand. So the reason why you see G here and G later is that we just keep it in the equations. And the reason is that if you want to extend this type of language, for instance, to include double logarithmic terms for event shapes like thrust, at that point that becomes relevant, and we know exactly what needs to be done for an extension in that direction. That is, you set G to 1 minus Z, which is the actual physical KT of the emission, and then you supplement the definition of the coupling with what is called the soft physical coupling that essentially has a perturbative series that involves the cusp anomalous dimension up to 3 loops. And the 3-loop term has a second piece that is proportional to the beta naught times the soft anomalous dimension. So with that very simple recipe, in principle, these equations should resum event shapes in a plus and minus at next to leading log. Now, doing that is, of course, technically challenging because the resummation in this context is more complicated than what you would have in other formulations. But technically, it should be there. So that's something interesting that one should look into.
Okay, thanks.
Right, so there is something that perhaps I didn't understand, sorry. In the single log case, right, you were able to write the equation a la Schauer, delta t over delta t prime less than a number, because basically you were able to say that the secondary splitting was negligible, right? So therefore you have that GG is proportional to U, effectively. Yeah. And I didn't understand whether you have already sort of reached the step where you're able to write something like that at next to single log, or you're doing that?
Something we're
because
working on.
It doesn't look trivial, right?
It's not trivial. I can tell you that much.
Okay.
So it's something we're working on. This for a little bit of time now. And yeah, it's tough. I mean, the problem of solving the next to single log evolution equation, this is the case of the quark, is considerably more complicated. You have these complicated contributions to the integral operator. So we had to develop quite a lot of technology to solve these things numerically, and something we're still working on, and hopefully we'll get there at some point. But then, of course, things. That example, actually, for instance, for the fragmentation function in the singlet case. And so you want to solve the full couple system, which is, yeah, exactly. It's very challenging, but
Yeah, I have a question on the extension of the method, because as far as understood, you could apply at the moment to observable that are just sensitive to this kind of logs, one kind of log. But suppose that you have observable sensitive also to other kind of logs. How difficult it would be, and in which direction are you planning to go?
Yeah, that's a very good question. So for now, what I just presented today tailored to the collinear problem. So it's not obvious that an angular evolution equation can be extended to describe, for instance, software variation. Right? In fact, we know that's probably almost certainly not possible. there are, so there's an equivalent set of equations that we developed, for instance, for the non-global resummation that describes precisely that soft wide-angle evolution. Is very orthogonal to this, and it's also very different since the object that the generative function is describing is the evolution of a color dipole. So it's in the planar limit, you're just connecting to two charges and that object. And you know, by evolving that, you reproduce the correct squared amplitude, which is a squared amplitude that is very different from what we need here. So how to put those two together is a question that is interesting to think about. I don't have an answer precisely.
Yeah, perhaps this was sorry, just an aside on this question. So in particular, and I think this is part of what Maria was asking, when you say there is another set of equation for soft wide angle, which is formulated in terms of dipole, the difficult thing, it seems to me, is the wide angle, in the sense that I expect that any such equation will also have a collinear limit, and there will be some double counting to subtract. Is that correct?
So the collinear limit that is produced by those equations is incomplete, or something well-defined, but it's not the full story.
Yeah.
And it will be overlapping in bad ways with what is described here, and so putting those two together, eventually it would be nice to have a single set of equations that, at least in the planar limit, interpolate between soft and collinear correctly. That would be a beautiful thing to do. It's something that then you could study showers more generally from
well, we can discuss that. So I saw several hands. I will start from here, and then I think the microphone can flow up.
So let me just follow up with this question because I'm still a little confused. So this looks a whole lot like an ordinary parton shower, except you get rid of some parts of it. If you just took your favorite dipole-like parton shower and run it to produce an answer for one of these single log variables, will it get the right answer? Yes?
the showers that are next to, they are claimed to be next to it.
Yeah, so just to give you a bit more work maybe, but so the setup seems quite general, so one could imagine doing this for next to leading log, right? There's more things to compute in the finite part,
Yes.
but, and to solve it will be probably almost extremely hard. But the calculations of the finite part, maybe even newer anomalous dimensions, is there a fundamental difficulty there, or are there things that?
Yes. Actually, and you will have now to extend the.
You need to arrange the subtractions from the lower.
Matching coefficient will be extended at two loops in general case, and then you have to extend this integral operator to alpha cubed, and it's just complexity essentially, because now you will have the 1-to-4 splitting function. You have to subtract. Here I was subtracting the double counting with the iteration of the 1-to-2. Now you will have to subtract the double counting with the double iteration of the 1-to-2 and the single iteration of the 1-to-3.
Right.
So there is, it becomes a little bit cumbersome, but in principle, one could write down an equation that in calculations is it's a different matter.
Yes, maybe a comment towards what Maria and also Lorenzo was asking. I mean, in principle, you can write these generating functional equations really for full set of momenta, right? And you go from one event to a next one and so on. I think that's something I've done only published in my thesis, but nowhere else. But the question is that, and it's actually something which you could relate to, maybe I'll talk about this on Friday, to the amplitude level case. If you think about the generating functional version of formulating the Jim-Walk equation, you get similar structures on the amplitude level. But of course the question is, to what extent can you factor these things into independent building blocks, right? If I only look at large angle soft, I can factor it into dipoles. And so I can use the implicit solution of the complicated one, factor it into generating functionals of branching a dipole into something else, at least in the large NC limit. But that's exactly the question I have. At what point do you expand things like a recoil mapping then, right? Where do you plug that in? Because in principle, this is obstructing the factorization. If you look at full sets of momenta, and you
That's
just
where-
have that beast sitting there for n and n plus 1 momenta, and it's not
That's
going
where the
into anything
dragons.
simple.
That's where the dragons show up. So the problem there is that if you want to, so one thing is solving these equations in the context of, you can solve them with a Monte Carlo-like algorithm in the context of doing a resummation. But if you want to build a full-fledged shower, you want to have full momentum conservation. So that adds an extra source of nonlinearity, that is, each branching has to restore on-shellness in the whole event, technically. And so now, how do you formulate a mapping, a kinematic map, including the one that I use to perform the subtraction of singularities, in a way that doesn't break this accuracy? We know that wrong recoil schemes break even leading log accuracy as a bleeding color. So one has to be super careful there. And right now, that is where, things are a bit of an art more than a science, in the sense that you have to be very careful. There is a lot of intuition. One can build the kinematic maps using physical principles like causality, or the fact that emissions far apart shouldn't affect each other. But there isn't a very systematic recipe. Starting from an equation, you invent a kinematic map that gives you a partner shower. All of this stuff needs to be understood much better. And, agree.
Thanks, Beck. Can you go to slide 19? So here you say that you have to recompute the anomalous dimension if you change the setup. But am I correct to say, if I say that in principle, if you have one, you can get the other ones just taking the difference because it should be finite, right?
Perfect, yes. That's absolutely right. And that's why we are optimistic that even if the shower has a very complicated mapping, so it will have some terrible B2 of Z, you can calculate the difference between this B2 of Z and the showers with a 4-dimensional integral over 1 to 3 splitting functions.
Thanks. And the second question I had, so you start having the subtraction terms that usually when we do subtraction can become nasty numerically because you get large negative and positive. Yeah. Do you see this problem, or this Cambridge-Arkin stuff is physical enough that protects you?
So it's also a very good question. So indeed, the counter term is organized in such a way that you subtract the singularities between the double real and the differential counter term. But you can have, for instance, additional singularities, for instance, where the emission at wider angles is going soft. Okay? And in principle, the difference between this integral and this integral, if, for instance, emission 1 goes soft, emission 2 is a smaller angle, so the singularities of emission 2 are cancelled by the counter term. But if one cannot go collinear because by definition its angle is the larger one, but it goes soft. And now the singularity of that soft divergence is cancelled by this double counting guy. So, of course, you can regulate the two with a slicing parameter Z0 and then cancelling, but that is a terrible idea. So in practice, you have to re-massage this K finite in non-trivial ways to get proper numerical stability in the calculation. This is a problem that was also there for the non-global case.
This particular plague is very widespread in subtraction.
But also good because there's a lot of technology out there that could be recycled.
Besides the NNLO DGLAP kernels, which I asked you about earlier, should you also be able to reproduce the NNLL resummation of the energy-energy correlator?
Yes. Yeah, although that has a more complicated structure than the observables I mentioned here, in that you cannot now ignore the subsequent terms anymore, so you need to.
So this was the grooming cut that caused you to be able to?
No, it's the type of observables that I was considering there. So for the energy, you can do a similar simplification. If you have a 3-point correlator, that is something that is it's a little more complicated. So
okay, I didn't quite understand what this observable was doing for you, and is it only doing it for you in some range of X?
Yeah, so right, X is a parameter that...
But for generic X, you get wide angles in there, right?
You would accept that you are applying grooming before you measure those observables. So grooming is
So
getting
grooming is
rid
also
of
important to
wide
getting rid.
angle. Yeah, exactly. Otherwise, it would be more complicated. So in principle, solving numerically those equations should, if things are done correctly, should produce EC at next to lean log. And yeah, it
Thanks.
would be nice at some point to try to do these things.
I don't see any further questions. Well, you had an application that you skipped since we are.
Oh, okay. Well, it was just the easy one. Application was basically recalculate these observables that I mentioned here to next to single log, right? This is the form it takes is fairly simple. Also at this order, you can recognize the matching coefficient at one loop that I mentioned before. In this case, we are considering two simple dummy processes like Z decay or Higgs decay for quark and gluon jets. So this C is just the NNLL matching to full QCD. Then this exponent R is inherited directly from the Sudakov form factor, which is supplemented with the observables constraint, both for the FC sub x and for the angularities, although I don't write it here. And then finally, you see the effect of this K finite term that leads to this clustering correction that essentially is coming from the soft limit of this object. And here again, the fact is that for these observables, due to the fact that there is this hierarchy that Lance just mentioned, at next to single log, I only have to consider one secondary branching, and ignore the fact, the cases where there are two or more secondary branchings at the same time, because those will be further suppressed in the logarithmic sense. And the effect of that one secondary branching is precisely leading to this correction factor on top of what is described by the Sudakov. Okay. So these are simple calculations in this case, but the nice thing about these observables is that thanks to grooming, is something that you can directly apply to hadron colliders, where now the whole process dependence is in this matching coefficients, and this will need to be replaced with a proper calculation with, for instance, the NLOZ plus jet production. Then it's convoluted with this prediction for this fragmentation of the jet. That is something that is independent of the Haar process. So some of the things that I would like to do is eventually do phenomenology of the LHC with this type of observables. And I should also mention that this is something that has already been considered in the case of angularities for quark jets in other papers, and there is a whole industry of predictions for this at the LHC.
Those are still groomed jets.
Yes, you have to use groomed jets, otherwise you would keep a process dependence in the calculation. So the plus and minus case will be different from Z plus quark jet, for instance.
Okay, I think we can thank Pierre. We grilled him enough. So.
Thank you.